air resistance, what is the speed when it strikes the earth? Well, an object is dropped from a very large height and is going to fall to the surface of the earth. We use the same principle. We find the potential energy at this height. Now, what is the equation for the potential energy of an object at a given height h? Potential energy is negative g MEM over Re plus h. That is the potential energy at that height. And it is dropped from that height. What is its kinetic energy? 0. It is dropped. Its initial speed is 0. So its total energy at that height will simply be negative g MEM over Re plus h. Alright? Now it falls onto the surface of the earth. What is the potential energy on the surface of the earth? The potential energy on the surface of the earth is negative g MEM over Re, which is the same as negative small g REM. Is that right? That's the potential energy. And when it falls to the ground, it strikes the earth with a velocity. It has a kinetic energy. We need to find that speed. Its kinetic energy is 1/2 mv squared. The total energy on the surface of the earth must be equal to the total energy at that height, and that is the method we use to solve the problem. The height from where the object is dropped is 5 times 10 to the 7 meter. The radius of the earth is the usual value, and the potential energy of the object at the height h is negative g MEM over Re plus h. And let's replace this GME. What is GME equal to? Small g Re squared. So that will be negative small g Re squared m over Re plus h. This is the potential energy of the object at the height h. What is its kinetic energy at that height? Is 0. We are dropping it from there. Therefore, total energy at that height is simply this value, negative g Re squared m over Re plus h. Now, when it reaches the surface of the earth, its potential energy on the surface is negative g MEM over Re. And replacing this g ME by g Re squared and simplifying, this becomes negative g REM. The potential energy of the object on the surface of the earth is negative g REM. And it hits the ground with a speed v, which we need to find. Its kinetic energy on the surface is 1/2 mv squared. So, if you now add the potential energy to kinetic energy on the surface of the earth, that must be equal to the total energy at the height h. The total energy when the object reached the surface of the earth with a velocity v, with a speed v, is its kinetic energy plus its potential energy. 1/2 mv squared plus negative g REM. It is this. And now, this quantity, which is the total energy at the height h, must be equal to this quantity, which is the total energy on the surface of the earth. Let's go to the next slide and equate these quantities. Now, I took those two quantities. This is the total energy on the surface when it reaches. This is the total energy at the height h. And we need to solve for this v. Can you do this on your own? Just like we were doing before, multiply by 2 and divide by m. So divide by m and multiply by 2. When you divide by m and multiply by 2, this term will simply be a v squared. What would this be? Divide by m, m will go, multiply by 2. This will be minus 2GRE. And what will be the right side? Divide by m, m will go, multiply by 2. It will be minus 2GRE squared over RE plus h. So, therefore, v squared equal to, now what I did is, I also did one more thing. I moved this term to the right side. So, v squared equal to, I'm going to write this term first, 2GRE squared over RE plus h, and moved that term to the right side, plus 2GRE, so that I have v squared alone on the left side. And now, let's put all these values. That is the challenging part, is that right? Putting them all on your calculator. Well, we know G, that is 2 times 9.8. Now look at the way I write the square of the radius of the earth. 6.38 times 10 to the 6th squared. You must do the same when you use a calculator. All over. Now, on your calculator, you must put this in parentheses. Very important. 6.38 times 10 to the 6th plus h is 4 times 10 to the 6th plus 2GRE, the normal value. Okay? Do that on your calculator. If you have trouble with it, let me know. I want to make sure that you can calculate these values on your calculator without any trouble. And that gives me v squared is 4.8 times 10 to the 7 meter per second. Therefore, v is 6,942 meter per second. You can see the method of all such problems is almost the same. We use the conservation of energy. The total energy at the surface of the earth equal to the total energy at other place, wherever that is. Now, we will discuss another important concept related to gravity, and that is Kepler's laws of planetary motion. Much before Newton came out with the gravitational theory, Kepler had done a lot of work on the way planets move around the sun. Now, originally it was the thinking that the planets moved around the sun in circular orbit. But it was Kepler who first came in and said, no, planets don't move around the sun in circular orbit. Their orbits are elliptical. Now, Kepler made 3 important statements about the motion of planets around the earth, and these are called the 3 laws of planetary motion. Now this is the first law. Law 1 says planets move in elliptical orbits with the sun at one of the focal points. Now, do you know what an ellipse is and what the focus of an ellipse? Well, let me see if I can take a minute to explain that to you. So, a circle is made up of a set of points that are equidistant from a single point. And that distance we call the radius of the circle, and that single point is called the center of the circle. What is an ellipse? In the case of an ellipse, we have 2 points. And if you can now locate the set of all points such that the sum of the distances from these 2 points are the same. In other words, if you take any number of points on the ellipse and measure the distance r1 and r2 from 2 fixed points, the sum of these distances will always be the same. That is the definition of an ellipse. And these two fixed points are called foci. Foci, which is the plural form of focus. So an ellipse has two foci. Now, what did the Kepler's first law say? Kepler's first law said a planet moves around the sun in an elliptical path with the sun at one focus. So the sun is sitting at one focus. What that means is, at some times the planet will be closer to the sun, some other times it will be farther away. Well, that is the distinction between an ellipse and a circle. So Kepler's first law, planets move in elliptical orbits with the sun at one of the focal points. Now here's an illustration of it. Planets move in elliptical orbits with sun at one of its focal point. You can see this ellipse, the sun is at the focus. The other focus will be somewhere over here. Alright. Do you notice anything that is significant in the motion of this planet? Did you notice that the planet will move a little faster when it is closer to the sun than when it is farther away? Did you see that? Well, that is a characteristic of the motion of planets along the elliptical orbit. Now, what is the second statement? The second statement is actually will lead us to that conclusion. Which conclusion? The planet moves faster when it is closer to the sun than when it is farther away. It says a line from the sun to the planet sweeps out equal areas in equal intervals of time. What is the meaning of that? If this is the sun and this is the planet, the line joining the planet to the sun will sweep out. As the planet moves, that line sweeps out areas. Now, a very important law, a line from the sun to the planet sweeps out equal areas in equal intervals of time. Now, watch this. As the planet moves around the sun, these shaded areas indicate areas swept out by that line in equal time. Now, you see why the planet has to move faster when it is closer to the sun. In order to trace out the same equal area in the same time when the planet is closer, it has to cover a longer distance. You see that? Because the distance between the planet and the sun is small, it has to cover a longer distance along the ellipse so that you have an equal area like you cover when it is farther away. That means the planet has to move faster when it is closer to the sun than when it is farther away. That is the essence of the second statement. You must be familiar with it. A line from the sun to the planet sweeps out equal areas in equal intervals of time. Okay. Therefore, the planet moves faster when it is closer to the sun than when it is far away. Alright, the third law, Kepler's third law is, it is a quantitative law.